seems like it is. Okay, so we're back to this bullshit. Made some changes yesterday after my electricity crashed, like actually in the whole block. A big part actually, was down with electricity, which was fun. Anyway, lasted a few hours, then it went back online, and then I found out that I was quite a lot of work. Luckily, I did save quite often, so I mostly lost just the latest PCs that were quite complex, but it gave me a chance to redesign some of the way I'm entering the opcodes for each instruction. So I ended up with this thing. Oh, I'm not sure if the music isn't too loud. It probably depends on the track. Yes. So yeah, in so the x64 binary and there is x64 OP unary. These two represent a set of opcodes for each instruction. I eventually decided that I will have just two general ones, where the first one is register on the left and memory expression on the right. And the requirement for it to be set here is that it must support 16, 32, and 4 operands. Same for the other way around. And then I have opcodes that seem to be quite consistent, at least between the. If we pull up this one, they seem to be quite consistent between the instructions. So at least mob, sub, and add would do these things. Can be split into these instructions with the same behavior. These instruction types or opcode types. There is a lot of details going into some of the encodings. So not everything is just mod RM and SIB. Sometimes the mod RM is used quite weirdly, which is especially with these two, where we, in case we are using these for register encoding, because some of the I have a variant for register IMM8. For example, sub doesn't have that variant. It only has RM to IMM variants, and if it's registered to IMM, it's only for RAX or A on 8, 16, 32, and 64. So I will have to encode these separately because them lacking actually the Reg 8 IMM 8 makes you use larger or longer byte sequence. So this is at least 2 bytes, while this is just 1. Plus, of course, the immediate value. So this would encode just the opcode and the operands in 2 bytes, and this would encode it in just 1 byte. However, for sub and add, these are only available for A register. So yeah, no fun there. I made it work. I will show you. Let me get to the point. So yeah, in this case, this is a logic for encoding register to IMM instruction. So if you have a destination for a register, well, it's not really destination at this point because, yeah, for sub, yeah, for now, for those instructions I made, it is usually a destination. So there is always a choice. If the size is requested to be S8, which is kind of way of saying that you want to force the encoder, it would be something like this. A minus equals 5, for example. It would technically force the whole instruction or whole expression to be in 8 bytes, in 8 bits. That makes it So in case the IMM, for example, say we had larger value larger than 255, we can go, I don't know, for 400. This will detect that, hey, the value is larger, but you requested it to be on 8-bit, and we will push out a warning. I'm not sure how the warning will be dealt with. I just push out printf, basically. Nothing fancy in there, but eventually I might do some additional work here, because this would be also great if you can collect these warnings somewhere, and they seem to be quite similar, so I wouldn't need to express them by string. I can express them by some simple value, because I generally don't like strings in libraries unless they are absolutely required. I generally like errors to be, or warnings to be encoded as numbers, and then the front end can do. Here we have the logic. So if we do have, I will open the second part here. We can compare mob and sub. So sub doesn't have this reg8 IMM8 thing. It's set to -1. I'm now using -1 because I made the instruction to 16-bit. Just because I can use -1 for saying, because 0 is actually used. 0 is actually here. 0 is actually for add instruction. So yeah, if it's -1, that means that offset doesn't have it, and we have to use something else. And that's RM8, IMM8, and these are usually provided. Depending on which type of opcode we have, we choose how we're going to encode it, because there's a difference between them. These reg8 IMM8 usually encode the register, or so far I've seen they only encode the register directly in the opcode, so its last 3 bits are used to encode the register. But for RM8 and IMM8 version, we have to provide the mod RM, and this one, this one, and this one are using. Seems they are using the some kind of weird encoding of mod RM. So how it works is that it would produce opcode. The first thing, obvious, we are not doing any changes to opcode. Opcode doesn't contain the register, but the register is contained in RM. It's something I found yesterday. Quite weird encoding, because RM would be used as a base. Kind of makes sense. It would be used as a base of the memory expression. Slightly makes sense, but hey, we have to set the mode to 1.1, which means register to register actually when we are using mod RM in its original context. We need to, however, encode extension to the opcode, because the instruction is not given just by single opcode, but you have to specify this extra one. I think we actually went through it yesterday, so yeah. This register field inside mod RM byte is used for it makes it kind of nice and it's more complex, but it makes it symmetrical at least. Like, hey, these are instructions that are encoded like this, these are instructions that are encoded like this. So yeah, there is probably a lot of historical reasons. I'm not complaining at all. It is what it is. Yeah, so this is how we have 1 byte for opcode, 1 byte for mod RM. I have to yet test whether there is a need for SIB. Not sure what will happen when we will use register as I think the special one was RSP or RBP. One of those is special ones or treated differently when we are encoding mod RM, but this case seems to not care. So I will check on that. Later we'll do the test variants of those special cases, and then we basically encode it normally. We put 1.1, this means 1.1 opcode X. We're adding +1 because mod RM will do -1. and check whether it's 0 first, then do -1 on it for encodes, and register all already comes in incremented by 1. What it's supposed to be. I'm thinking about changing the registers to be actually -1, but 0 is nice. Having default 0 as none is good, because then you don't have to specify it when you're using the APIs. So the API, you don't have to do something like this, which wouldn't be that much of a problem, but with memory expression you would have to go -1, and then something else, which would say that, hey, I don't want any base, any index. Not sure. Maybe it will make sense because I'm using already that for opcode, but for registers for now it's just 0, and I don't care too much. This one is even louder. Hey, Ginger Bill. So yeah, we are in this rabbit hole. Rixie cannot stop laughing at me. Which is, yeah, I mean, I cannot say anything against that, because I trapped myself in this rabbit hole, and I'm trying to find my way out. So yeah, this is where I am. At the moment, I was running tests for variants of sub, where we have memory on left and immediate on right, and register on left and immediate. So these are basically register on left, immediate on right, and then we have also expression like sub RAX or RCX plus RDX times 3 plus 7 is 5H. I'm using 5H here because 64. RDX. So yeah, this will basically take the value in the memory at this calculated location and then decrease it by 5, what it is. So you can not only decrement or subtract from register, but also from memory, which is quite interesting. Not sure whether I will use it, but I'm trying to make the library as complete as possible, at least for these instructions that I will need. So yeah, I'm now having problem with this one. It seems to be producing something different than what we expect. It seems to produce 83 here and not 80. So I'm in the middle of that, looking at it. But because I already know that the code worked for mob, then it probably means that I really have just wrong opcode here. So we can run it, and we see that these two are okay, so we produce these two okay, but the opcode is incorrect. So I will go through, check whether it actually goes to which instruction it eventually ends up using, and whether it's correct, just to make sure that what I expect. We will get IMM size. I will open the debugger here. So IMM size would be 1, so that's 1 byte, and it's correct because 5, so that's encodable by 1 byte. Size we are forcing to be also 8 bits. IMM size, yeah, this is in case of we need to truncate. IMM size is 1, 8. For sub, it seems that it correctly branches out, because then we can look at the opcodes here. So opcode for register 8, IMM 8 is -1, so it's not set. That means that we have to go to the branch. When we go to this branch, it says 131, which is 83. So we need to make sure that check whether 83 is actually what we expect it to do, because ML64 seems to do something different. So we go here to the manual. I will zoom it in a little bit. And in the manual, you see that 83 is actually the generic one. It's this is instruction that I would say is Not even from these. There is a opcode for the, yeah, it's this one. Have anything? I will just write it here. This, yeah. We are not even using encoding these, but this is not used. Not sure what's the use for these in these contexts, but we will see eventually what it does, because it's moving the value to 32-bit memory location. Yeah, it makes sense. So if it's a memory location for register, it doesn't make sense, because for register you probably want these. But if you want to write it into memory, or use the 32-bit or 16-bit or 64-bit value and decrease it, subtract 8-bit value from it, then these would make sense. Yeah, so this is okay. Yeah, so I will have to plug them in. I don't do it now, but these are really missing. This is something I will have to do, and will probably do it even today for these cases. Already write that expression here, so we can test it next. So we want the 32-bit value to be set. We want this to be in 32-bit mode, and we want it to be in 64-bit mode. And then for RCX it should be okay with sub, because and we will see what it is. We wanted to at least return the 83/5. So this will be 83 at least. Yeah, correct. But it obviously means that in the sub instruction, when we are trying to do the logic, then or mean the mapping, then this is not correct, because correct one would be RM8 on left and IMM8 on right, which is 80/5. So we need to change this. This is 80/5, and I will already do the RM IMM8 version here, which is 83. 83/5, and this 81 is also over 5. Okay. Yeah. Okay, I will do. I will do them, so I will remove. At least for sub, then I will have to find it for here. So this should fix the problem we had. This should now produce pass and produce this 80E905 byte code. Yeah, does pass, so that's okay. And then we will do these two. So this is fixed. Let me now run the subset of the tests. It actually crashed the compiler yesterday. I wasn't able to compile it with 16K tests. I will have to probably split it up, because now it produces the test for everything into one file, but eventually I might want to split it up by at least instruction. For that I will have to change my generator code that is writing these things, and probably return just these binary things and things from this code. Yeah, so it seems that the tests have finished, so we now confirm that binary encoding for sub instruction in all possible modes, because now we have, I think, all of them, except for that one instruction, of course. So for that in one instruction I will have to tests for RM IMM8. So I will have to generate tests for these. Okay, so let's test it through. Let's go through this, where it will go, and we have to find a good place to play. And I'm actually quite happy with what happened yesterday, because it made I found these special cases. Oh fuck! Yeah, it's compact. So it made me step away a little bit. So it was kind of good that made me step away from the and realize what actually happened. The only thing I hope is that there won't be any or too many of critical cases for different instructions. Somehow hack around in existing structures. I hope that I have covered everything, because if you look into sub, except for these, I have encoded every one of these instructions and I'm actively using those. So let's go. We have 80 done. 83, let's go one by one. 81, it is, and it is used. You can also check it. Yeah, it's used here. Then we have 28 here, and it's used with RM8, Reg 8, and that's just that case that we went through right now. Yeah, it's not. This is actually not used for a funny reason. We use the other one. This is not used because ML64 seems. There are two options actually. You can encode the same thing if you are going register to register. You can encode the same thing with two different opcodes. And GCC seems to prefer register 8 RM8, while Microsoft's assembler seems to prefer this one. So I left it for this one, but I have a switch, so I can switch to GCC mode if it will make sense sometime. There might be times when I will switch from using ML64 backend for generating the and use that. We will see, or maybe some other assembler that I can pack with the thing. Because, for example, Microsoft's one I cannot use on Linux. So if my library will be used by somebody who is on Linux, you won't be able to get good output from tests, because he wouldn't be able even to run assembler. That's the first problem. And second problem, even if he ran GCC, anyway, let's go back. Oh my god, I'm talking too much. So where were we? So 28, yeah, that is used. 29, yeah, that is used. And these are the most important ones. Basically 2A, yeah, it's there. And 2B, yeah. So even if I thought originally that, hey, I will just need like one, give me just one, some general one, I eventually needed to use everything. First reason is that especially these ones are required, because these are two different operations, completely different. They are null optimization. If you want to use memory on left, then you have to use these. Then these and this is also, this goes with it. So these 80, 81, 83 are required. Then these RM8, R8 are also required, because you want to be able to subtract memory and or register from memory. And it also goes for these ones. So this is the same idea, except here you subtract the immediate value, here you subtract register value, or value and register, and here you have it the other way around. So there is no like not a single instruction except for these that wouldn't make sense, and that you can basically just skip somehow. You can technically get rid of 80 maybe if you force the immediate value to be truncated to 8 bits, Sorry. Same for the register, but with the register you would have to have additional AND instruction before that to make the code even larger. So they are kind of optimization for some cases, these ones with the IMM8, because you can just use 32 at the worst case 64. 64 version doesn't even have like a version of IMM. This is quite interesting. So yeah, you have to use basically all of those in order to produce something at least a little bit reasonable. Then of course there are special cases like resetting or setting 0 to registers that you can replace with XOR or something like that. So those, I'm not sure whether those should live on an assembler library. They should live somewhere else, maybe some additional library that will sit between you and the assembler library, and will choose better instructions depending on your preferences, and you will have an option to switch it off or just bypass it and generate the... Okay, so we fixed that problem, and now we're back at this one, and we are trying to encode the RM IMM8 thing. So the size would be 32. It's here. But the IMM size is 1. So in case we are in this part of the world, this is special. So yeah, it's just this one. So in case we are here, if IMM size, because here you see that even if it was larger than 4, then we would produce a warning and force the IMM size to be 4, because we are using the IMM32 versions here. Both of them are there, so eventually this will encode the IMM value after. But we cannot do that in case we have the instruction for RM IMM8. So if IM size is 1 and we have RM IMM8 instruction of code, then we can still do encoding with that one. Yeah, this warning doesn't make sense for the first case, because we know that IMM size is 1, therefore we can use this this variant. So here we need to, this is RM, that means that we need to use this type of encoding. We're forcing 32. Yeah, size is 32. That means that, at least for now, the sizes are a little bit weird. And we do RM IMM8 and RM IMM8 op and destination. So yeah, we should eventually end up here. Yeah, so we are here. Get in. Opcode extension is correct. Register is RCX. Yes. Yeah. 5. It actually clashes with that. We should probably use something else there. Opcode is 131. That should be 83, right? Should be 83. Yeah. 83. I'm thinking whether there is... Yeah, we'll finish this one. I move. Yeah, so bounce. Use E3E905. This is exactly what was produced before by the error case. Incorrect case, yeah, so this is correct. It's 32-bit register used here, so it's no longer CL05, it's ECX, and we're subtracting 05 from it. That's awesome, and that is also a case when we want to do... I will test it for 64 as well. I need to get the... so yeah, this is correct. I will put it here. I will try to change the generator to then we have a variant with R9 as well, and this will be with yeah, I will keep it like this, and R9 because R9 is a sort of extended register for the platform. And then I wanted to do memory, RCX, x64, RDX, for example, X1, X2, for displacement for the memory part. So that's like the next one. I assume this will work. We just need to fill in these things, and I need to make sure that we are actually generating those. So when we go here, this should go to a different part of the code. Yeah, it will go to not to register memory or register IMM as before, but it will go to memory IM. And here the deal I think is the same. No, it is not. This is structured differently for some reason. We'll have to restructure this to be rather the same as this one. Although this is doing much more things in there. So IMM size is 1. Yeah. I'm not trying, I do remember I was trying to do something with the defaults here. In case the size is default, it will do whatever it needs to do. But I'm not sure what I was trying to do. So I will have to rework this piece of code to similar to this one. Because this one's structured, especially for these kinds of changes. Okay, I'm going for a quick smoke, and then I will restart this function. See you in a bit. Okay, and I'm back. Okay, let's do this stuff. So I will do it the same way we did it before. X is not needed here because I moved all the encoders to separate functions. Do this. So if requested size is, or size override basically is 8 bytes. 8 bits. Oh my god, I still keep doing this incorrectly. Then we go here, and this is what we do. Else, only in case the IMM size is larger than 1, we will produce warning. We are truncating it. Else, if size requested is x64 32, I'm not supporting 16 yet because I think that requires some kind of a prefix, and 16 will save you 2 bytes on the immediate value and will make the instruction faster, so will save you 2 bytes, makes it a little bit faster, I guess, or maybe even not with L1 and everything, doesn't matter, because it will load the cache line. Unless it's at the end of the cache line, so it may there, but yeah, so it will save you 1 byte, but because that 2 bytes, but because you have to do prefix for it, I don't know, but I guess done by a prefix it will save you 1 byte, so its use is rather irrelevant really, or really small optimization to this with requiring a lot of code. So probably I will even, because of simplification, I will probably go less right now, and eventually we can edit for complete, but for now we'll do. So if the IMM size happens to be user requested size to be 32, so he wants to subtract 30 from 32 bits in memory in this case, but he provided immediate value small enough, we can optimize on that, because yeah, it means that otherwise he would have to somewhere cap it or truncate it itself. So here we will do a different kind of instruction, and I'm not sure whether we can do this one actually. Here, I think we should that. And it almost starting to seem like we can do this, and always on. This is S32, and we have RM to IMM8, and then these are the same. Okay. Otherwise, we are in 32, and in case he provided more than immediate value larger than that, we can produce a warning. Force the size. Yeah, we need to force the size here as well. IMM size is 1. We'll write the later. IMM size is 4, and we will do this. No, we just do the same thing again. No, we need to use one of the other outputs. So the only, yeah, this is the decision, and it differs only on whether you're using R32, yeah, which instruction we are using and which extension to the instruction we are using so far. So yeah, this is all okay. Else, if you request a different thing,
Let's play.
and the IMM size is larger, this is 64 bits. I will write it here, and we can actually check for that. x64 S64. So with IMM size, immediate value. I'm now thinking if he produced this one. So if he is trying to set 64, force us to be 64 bits, but we cannot do that because then there are no instructions in general. There is only one, and that is the mode for this case. So in case we are doing this thing, and he's trying to do the memory, MOV even doesn't have the memory variant of that. So if you go back to MOV. So only case when it accepts IMM64 on the right, this one. Only one, and everything else is accepting only IMM32. And then it signed extends it to 4 bits. And this is happening for sub and add and everything. So the only way you can actually subtract 64-bit value is by going through an actual register. So first you store it in the register and then you call the 64-bit register variant. And so if you want to store 64 bits into memory, you first have to set the IMM value to register, and then you would call, where the fuck is it? I think it's this one, yeah. So this is how you then can store 64 bits into memory. So if you are using immediate values on x64, there are 64 bits larger than your compute, lower than it was just a compute, because it has to do 2 operations, plus it will take one register away, and compiler has to work around it when he's allocating register to compensate for that, because now he knows that, hey, I will have to use some register here because of a fucking IMM value, so he has to compensate for those, which of course will produce less optimal codes. Unless of course the register is free and he has a register available. The function compiling is rather small, or doesn't need to use many variables or intermediate temporary values. So okay, so if the size is 64, then we are storing to memory, and we cannot because we don't have any instructions. So in this case, if it's x64 operation, not M64, IMM64 is not supported. And this is actual error, so we will set it as error and return null. This will tell the rest of the code that, hey, we have error and we have to for the user. Cannot do this thing. I will have to check what it does when it's doing sign extension in here, so we are correct in those, but sign extensions and dealing with signed persons I plan to do later, as this will be also part of a larger test like arithmetic picture, dealing with the correctly. Okay, so this will fail here, and then we need to do, and this is not. Yeah. Okay. And now, let's optimize this, because we have 3 calls that only differ on size given by size argument. It's all, we already know what it is. We don't have it that way, and it differs on this differs on this pair. So what we can do is have opcode initialize to -1 and opcode extension, which will be for now 0, initialize to 0, and we can just do that. Opcode is this one, and opcode extension is this one. We can move this away. Should have tested it first though, whether it works before I optimized it. I think I will pay for that. I'll do it a bit later, but let's assume that for once I was right about this thing. So this is this instruction. This is this instruction, and also the layer that actually produces like this advanced or more optimized code for some cases, like setting register to 0 or some stuff like that. Also be possible to deal with these cases. So if you yeah, I won't. Yeah, I thought that I will be able to, on that layer, be able to deal with this 64-bit case where I would just store it to a register, but that fucking thing shouldn't actually use register just like that, because it's a register allocator that should be in control of when and how a register is used. Otherwise it will fuck it up. So yeah, it cannot be done on that layer. So that layer only so far has only one use, and that's optimizing instructions for XOR or for divisions that are immediate on the right, immediate power of 2. We can do shift, something like that. Yeah. That case way, and that's it. So first part basically just selects which opcode we're going to use and what's the opcode extension, and then we will just store it here. This will be size, and I will do default here. I will do default here. I have to deal with that later to do check whether it has default works here as it's supposed to. I'm not sure what the default will be used still. So it's used somewhere else as well. I believe, yeah, this is the only case when we're using this one. If we are going for unary expression with memory, push or pop. So I guess we probably won't even need the because this is just saying for this case. I'm not sure if the case is. This is just saying for this case that it shouldn't produce the REX at all. And also, yeah, it shouldn't produce REX for size reasons. It can produce it for extending one of these 3 registers.
We knew
Yeah,
you were
these 2
here and
or
wouldn't
4
be able
basically.
to resist the temptation to solve the mystery of Phoebus.
Yeah, we will see that. We'll see whether it makes sense and whether we can get rid of it here, and therefore we don't have to anywhere else. And actually I can, if I don't do it here, then we will probably catch the king. And I'm not sure generally the default. Sizes, yeah, we are not doing the default. Okay, I will just leave it here and it will fail here. This is correct. This should be here. Yeah, because this is the size. We we can do switch case here. I like switch case. Not sure why it is. I like it so much, but I like it. Maybe it's purely for syntactic reasons. And I can actually change the codes in there as well. Yeah, but otherwise, if yeah, this is also the case. I think we should do it like this, because we can do 64 size as long as the immediate value is not. So if we do 64 size, if we do request 64 size and the IMM size is either 4 or 1, then we should pick one of these. No, we cannot. It's 64 and the IMM size is 32-bit, then we should use the 4. Yeah, that's what needs to happen. So it's not even one of these, because that's a separate instruction thing. Yeah, because here we have to use RM for IMM32. And I don't think that we have that one. Yeah. Yeah. We need RM32, RM64, and
I'd worked for this older man. Once he told me that he had spent all of his life thinking about his career and his work.
This is not correct. Only
that he had never really given anything of himself.
RM32.
His life was for no one and nothing.
IMM doesn't have it.
He was almost crying saying that. You know, I do believe there's any kind of God. It wouldn't be in any of us. Not you or me. It just seems space to me. If there's any kind of magic in this world, it must be in the attempt of understanding someone, sharing something. I know, it's almost impossible to succeed. Yes, really.
This is the same
So it must be in the attempt.
as the RM32. Same. Oh, it's the same as. This one shouldn't. It should be this. Because of code must support 16. For reference sizes. Yeah, so that's the one we will use. So yeah, probably we were right here. So if it's 64, then we basically do the same thing as we would do here, except we need to produce the REX thing. So yeah, I will leave it here. This seems to be correct. Fall through, as we will use RM IMM8 or RM IMM32. The breaks we used for E used. Yeah, so the REX will be generated by this thing because the size is 64. Only in case the IMM size is larger than 4 with this thing. Good. Yeah, this seems okay. I will need to also check up on the other thing where we copied this from, because it seems like we need to change some things here. Yeah, this is registered to I will do switch case here as well. And we need to change that one case. So this is S8. Break case. Much easier to read as well. Okay. And we do this the same way as we did before. Okay, so in case we are requesting 64-bit operation with register to INOM to register to be then only in case if INOM size is 8. Are we using larger than 4? Yeah, we're using larger than 4. So if you're using x64 INOM size larger than have to just indicate that. Here and here I will need to generate special cases when we do want 64, so to do binary array, binary ME. We need variant where size is 64. But immediate value is longer bits, 32-bit. I think this is actually very close to 2. And yeah, this is immediate. We will do it for registers as well. But this fucking thing. This will do all the immediates. Yeah. S64. We'll do the register here and the immediates like that. So that's the case. And then the special variant for mob. And this also push out C. Still format. God, I'm so not focused on one thing and doing two things at once. Okay, 64 S, and this is register on the left and immediate on the right. Okay. And this is operation size register immediate. Okay, this will generate the variants where the size is, the size is fixed here. We will do it here Yeah, we can do this like this. Let's force it so it's clearly visible when I'm looking at it. Actually, produce warnings, but it should be able to act those. Yeah. Because we also need this for every size, because we are able to produce it, but I'm now not sure whether ML64 will be able to handle that when we are doing CL and mediate is 22-bit. I don't know.
You were right. We can't hide from the world. We must live in it. We must search for allies, kindred spirits. And sometimes we must take chances like we did tonight. To do otherwise is to remain forever alone.
Generate the immediate. Depending on whether we have it, we call it true, and true will generate immediate for 64-bit. In case this is true, so this will go for 64-bit. Sizes will also go through all the sizes. So that means, but this is by size, so it generates correct IMM value for every size. But this one is generating a different EMM value. All the immediate values just for one side. We are able to encode also lower. I'm not sure whether we should even truncate it. We'll see about that. So for this one, this is memory immediate. Do probably similar thing where we copy this one. Go through not the sizes but the immediate values. Immediate 32. Size will be fixed to S64, and immediate value won't be calculated like this, but it will calculate. Yeah, it will be given just by the. Yeah, I mean. Yeah, okay, so that's it. Okay, so that's done. This one's done. Fall through. This one needs a cleanup here, so we are only writing that one. Yeah, this is using two different encoders, so that's okay. Okay, I think it's okay. Let's go here and check how it produces. One undefined. Goes from 120. Each one. 2, 6, 7. Goes here. That, yeah, that is not here, so this should be. Did I do here? 4. It's fixed, yeah. Yeah, it worked. Okay. So let's try this one, especially this single line before we run all the tests for it. So we are in a 64 branch. code. Immediate size is 1, so we didn't have error. And we are choosing RM IMM8 variant. Yeah, because we just, yeah, okay. Yeah. Yeah. Looks promising. Yeah, so this is what we produced. Let's check what the assembler says about it. Yeah, so it's keyword. So it's 64-bit. So 64 bits at memory location. This one, RDX, RCX plus RDX times 2 plus 4, and we store just a single byte. Yeah, that's correct. Wait it. Okay, so that seems to be working. Also need to check for whether these are covered by tests, and we do that by simply test. What we do? No, we will do it here. So we want this to be checked. We want this and this. Yeah. Breakpoint, yeah, it's just a 3. So I'm adding breakpoint everywhere where I want to murder that code. Bold. And this is the register. And we have the special one, and there is this special variant, but I don't think this will be called 666. This won't be. So every time you stop at one of these, you remove the breakpoint and let it run, let it continue running. And we are testing for sub right now, but eventually we will also have to test for. I will do mob first because mob has more options, more things, and also producing that 64-bit variant. So actually, currently every of those 6 should be called. If it's not, then we will have to amend our test generator. Okay. Nil here. First register case. Mem IMM. It's this one. And the first register doesn't see me. Oh, yeah, we forgot the size in there. Go away. Yeah, this one. Okay, let's see whether we will fix it by just build it. Yeah, it's fixed. Okay. It's taking a while. Quite a lot of tests. Only this file has 22k lines for all the tests. Yeah, so we hit the S32, which will use the RMM8 variant. This is actually 0. This is weird. Okay, so this one is not set even. To fix it. This mov, yeah, we didn't set it for the mov. one as last one because this is special case and these are general cases. So RM, IMM8 we are missing. We only have RM, IMM2. So for move instruction, we need these, not these. These. IMM8. That's C6 or B. C6. I think this first one is. No, this has to be. This is just the. We have the even. Don't think it. So we are looking for everything that has IMM8, right? IMM8 takes register. IMM8 and the register. We have register 8, IMM8, yeah, this one is covered. Yeah, don't have this for more. So in this case, we go to -1 because it's not supported. Only for sub. So we are gonna put a little bit. Yeah, so you can see that. Also, what's quite weird is that. Remember that I need to be setting those to -1, otherwise it will produce zeros. But it's okay because we should be covered by tests. So if we make some fuck up, hopefully the test will hold us. Okay, so let's run it again. So for more, we don't have that instruction. That means that I will have to test it for sub as well. That one particular thing has to be tested for, or I have to check whether I built there. Hold on this. Oh, this is 64. We produced one without them. Oh, I see what's happening here. Okay. Okay. So this is registered to immediate. And they did produce 64-bit variant for it because it has this REX prefix, but we didn't. I'm pretty sure we actually fucked up the instruction. Still okay. Okay, tickets. I will have go for a smoke here. Then we will debug this. Why? What is happening? Luckily, we have everything covered by tests at the moment. So if we fuck something up, still be able to high quality the library of them. So every case is tested and checked against actual level assemblers. Even if we have a lot of bugs right now, we obviously seem to be catching them so far. Of course, the quality of tests questionable, but I'm sure that we do cover everything else. So what I will need to do eventually is do some makeshift coverage coverage statistics here in x64. which will basically for each branch have here. We will record whether we have hit it with the tests or not. It will at least give us an idea about, hey, we have at least hit these branches. It will not give us an idea whether we hit all the combinations of branches possible, but it can give us at least any idea about hitting everything. Eventually, what I will do and we'll have to do is, when we produce any code from this, whether it's through language or through whatever, I will have to have a way how also produce actual ASM, so assembly code, these kinds of things. So translate this, what I already do in Lua, I will have to in C, so I will have to move that code from Lua to C. C will be able to generate these things for us, and then we can save it to a file and do the same thing we did before, so we can do binary comparison between our code and what we produced and what would ML64 produce in assembly, and it has to match. That's the first thing. It should be fully compatible with ML64, like one-to-one. We need to know why ML64 is doing these things, and then yeah. Okay, I go for smoke, then we debug this case. I think I know what's happening, but I'll see you in a bit. Okay, and we're back, so let's debug this. We should do something fun, to be honest. Right, how doing something interesting, and I will probably do that when I get. So we go correctly to the branch. We check. We want 64 size. So the 64 size of 0. That. Let's see. So MM size is 1, but we don't have any. Don't have. Go next. They actually used C7. I will check what C7 is. Which version we should, which branch we should take. IMM30. But I think, yeah. So we also have registered to IMM30. And I think we will take this branch. We'll check whether this one is correct. This is registered to IMM32. So register MOV and IMM. And it's B8 here, so that should be correct for our part. Well, that should be. They are choosing different things. They are choosing C7 reason. They are choosing C7, which is this one. And I kind of don't know why that is. I think why that is. I think I know why. Because this is a special case. Because if we put the Rex in, then it's this variant. Because it just upgraded that version. So we have to choose this one. You know. Otherwise, you would have to encode zeros. These. So IMM size will be fixed to 4. That's correct, I guess. Yeah, they encode 4 there. And we will choose the variant, not correct. We should have a condition here. Don't choose the branch in case the size is. If size is 2. We are not taking this branch in case the size 64 falls through here. Otherwise, we have to encode IMM 64 even if it's way smaller. Yeah. Yeah, so we will take this actually same thing. 184 should be 8 decimal 184 8, yeah. So we should take this branch would have been taken here in case the IMM size is large enough and we don't have any option. But because this one the same code, then we need to only limit it to 32. And in case it's not 32, it's smaller, then we have to encode it like this. And this will probably produce larger, or yeah, slightly larger. No, it will produce correct one. Or wait. This is, I wrote it different. Yeah, it's the other way around. So if we Yeah, we don't have to, we should not take this 184 branch in this case. This one, this is the branch we should, because now we will take it the other way around, so it's this way. So in that case, I can just change them like this, and we should be okay. Yeah, we should not take this branch at all. Take this branch, produce 199, 199, 7, which what they chose here, and encode mod RM with it, and that should. Okay, so let's do it again. Also, I need to turn off that. It's annoying to see there. These turbos. Let me see. I don't like seeing full command line. So we go here. We take the correct branch here. The IMM size is now 1, and we request 64 size. So we want register to be 4. IMM size is not larger than 41. This branch IMM size is 1, but we don't have fraction defined. Subcode IMM size is larger. We don't have to truncate it. We force it to 4, even though it's 1. Probably there is for zeroing, and this would be the perfect case for zeroing things. And I'm glad that ML64 is not doing the optimization for us in these cases, because it should have or could have taken like the XOR or AND or something like that, or subtraction. So I'm glad that they are not taking that for us in front. The only optimizations actually is the ones that we want to do, using the smallest possible, shortest possible instruction arrays. So here size is 64. So we will not take this branch, even though this register is defined. So we jump here. We force the size to be S32. Yeah. Well, I think we might. I don't think this will be. In this case, we should. Yes. Here, so S64. 64, and this is the C7 one. So what will happen? I will check the C7, and with Rex, exactly what we want. Yeah. So we don't encode Rex and don't use extended register, and the Rex there. So we will fail again the test. We will produce the same thing, the correct thing here, but the 48 won't be there. So that's my prediction there. Will happen. It's good to be able to predict your code. Yeah, exactly. So we are missing the 48 there, and that's exactly because we want the 64 version of it. We are part. Want this part. We want the size to be here. Use x64 S64 size. Here because we want X in this case, in case we fall through from sizes 64 S64. It's a little bit fucky because then have to thinking. Yeah, because we are reusing code here. Code reuse for. Otherwise, you would have to copy the logic here. Although still might do that. Code will be much easier to read right now. But yeah, I will do it like this for now. And what I will do, note x64, s64 falls through. Falls through here as well. And I guess that this will be also problematic with the second thing. One, because here we would have probably not, but it seems like something. We will use the actual size here, so no, it should. We are encoding here. This is different code from the other one. But this one only has one encode. So this one, because there are two different kinds of opcodes. Coding here. Okay, this should be okay. Let's run it again. Yeah, so we are falling through, going here, and here we put size for 64-bit size, and go back, and we should, yeah, we passed. So let's go back, remove these. I can kind of understand now why there isn't like a library already, or I wasn't able to find one. It's like there is none that is well known and used, at least in a handmade network. This is fucking shit to deal with, man. We are only dealing with integers right now. Still have to do all these floating points, or floats and doubles, and also SSCs, all the intrinsics and shit like that. So that's going to be really interesting. Okay, so we are hitting this branch, so we will remove the. Yeah, we didn't hit this one because we don't have this thing defined, but we have passed all the tests. So that's great. I will keep the bookmark, I mean the breakpoint here. And I will run it over a different set, and that's for sub. And then I will run it for AND, but before I do that, not AND, but add. But before I do that, I need to make sure that I have it set up correctly. So sub for add, we don't have this version, it seems, but I will check that again. Let's check that again. For add and add. So we need version for RM on left and 8-bit So it's this one. Yeah, it's the one we want. 83 and use it. So yes, that's the one. RMIMM8 up extension 0. Okay, so in next we complete now. We closed. Let's do sub now. We will check whether we go through all the possibilities. I think most of those branches. If we didn't, if we don't do that, don't hit them, we need to make sure that we fill in our tests. Also, I'm sipping on my delicious coffee. delicious instant coffee. Yeah, so we hit this one. Good. Remove it. And we fail on this one. And this is similar case, right? Stop RCX from this one. And I guess this will take a different route because one will have some of those actions. So let's do this one. Yeah, they are producing REX here, so this is probably the same thing. What do we, yeah, we are not producing REX for this case. Obviously, we only do the last 3 bytes at a time. So let's go here. Here. Okay, so in this case, we fall through here, we also need to use ice. Yes, only case when we are using S32 here, but we can actually put here. We know that its size will be S32, but I will leave it like this for now. I'd rather catch it with the tests. Yeah, passed. Good. So remove this one and enable the tests. Again. Frankly, I don't know what I would do without the generator, to be honest. It's a little bit too fucky. All these combinations, especially with all these addressing modes that they have and encoding variants. So I'll gladly wait for it to compile because that just saves so much time. Okay, so we're hitting this one. That's correct. We're hitting this one. That's also good. And there are some branches that we probably didn't take. Now these two. So we didn't take this one because, yeah, that makes sense. Didn't take this one. But I wonder why we didn't take it with MOV. I will keep the bookmark here and go back to MOV, because this one should have been taken somewhere, and if it's not taken, then we don't have it covered by tests. And the second part, this one, the immediate value being truncated to 32. Or whether we had probably we check whether this is mem IMM this case, and here we should have produced that case. Yeah, but this is immediate 32 only. So I think this should be really error, because if somebody passes in the correct thing, a larger value that we cannot do, and we would have to truncate it and maybe even sign extend it, then just stupid, and we shouldn't do that. We shouldn't do JavaScript here. Shouldn't be too smart about these things. So this will turn to this one, and let me see where we have warnings used. Yeah, this is also error. That's obvious that error. We shouldn't be doing warnings in these cases, because then they should fix it, because they should be aware of limitation. We're not trying to solve the limitations of the thing, trying to solve the encoding part. Only thing that this correct behavior. So return null. go through and don't do, you can ignore it completely. Yeah, 32. And I will have to change that. Warning is here. This is again error. And now we are not using warning, and I can remove this one completely and also remove it from the test so that the garbage doesn't pile up. Really? And yeah, that's it. Okay, so we need to test the MOV with gaze. The register is on the left. This will do only 32-bit immediates. Need to IMM by size, but we are not passing the IMM argument. IMM by size, we wouldn't pass the, yeah. So, and I don't think this even makes sense. Doesn't, I guess. I guess because we don't want the 64-bit to be passed here even, because that would be error case and different thing. So I will do just this one, and I will just compile it, and I would like to see that immediate used. Actually, so let's find it. Where are you? Here you are. Okay, and it's not encoded at all. It's all registered to immediate, but we do use, and it's quite weird. Well, we have just RCX, and then we have different sizes only for, yeah, it's 8, 8, 32, 464 zeros. Then we have 464 again, which I guess this should have been thing. Here we have 5, but with only 64 and 64, and never, for some reason we never go. Okay, so there is a bug in the generator as well. I messed it up. Register to, so we go through all the sizes and we generate the size, the IMM for the size. And if we return non-nil, then we should get that. So I will put it here. IMM size, I should have checked on. So if the size is 8, yeah, we don't do zeros as total function binary A would be just op ZREMM, and this generate this thing, and also out, of course, out after everything, so it's last argument technically, and I will do it differently. I will just fucking list it. For all sizes, yeah, we don't do iteration over sizes. We won't do iteration over And here we want operator this, Z this. Z will be x64 S8 with this register. And we will do it for all the immediates. Well, no, we only can do it. We will do it for 0 first. And the immediates are encoded. Yes. Want it for 0. Maybe I will keep the loop. And out. Then we want it for 5 as well. Then we want S32 and 32 0 5 500. We want S64 with the same ones. S64. And if IMM64 is set, then we want this one with actual 1, 2, 3, 4, 5, 6, 8. And this we don't care. Every register. Yeah, we don't. 1. Yeah. So S8 is only for 0, 5. S32 is for 0, 5, 500. Should be able to handle. 64 is only for those because it should be able to up to immediate. But MOV instruction has special. So let me generate it. Yeah. Yeah, so 0, 5, 0, 5, all of 32s, and then 64s, all the way. Yeah, that's for a different. Yeah, so the RCX and nothing else. It's the thing, even in size. Okay. Run it. Now it should hit the breakpoint. Yeah. We'll see whether it's correct though. It's not. Actual error. What did we do? What did we do? Yeah, we need to break here, right? Because dealt with the case. Again. Yeah, worked. Amazing. So I will try to do the same for sub and add as well. So this will now contain the sub and the end. Yeah, it worked. This worked. And then ME for sub and add, whether they work. And also I will check the code because it seems like we are writing all the things. Okay, it worked. So we have S8, all the S8s. Then we have no base, no index, scale, so just the displacement. Yeah, same thing. This is with the index with a larger size. Here we add the the larger size. Yeah. Now we switch and register, so we go from 0 RCX RBP R9 index. Next we 0. Now we will add base. All the cases with that, we are still on size 8 in here. and we will, as we go through all these registers, all the variants for switch to 32. Nice. 5, 6, 8, 32, and 64. Okay, seems okay. Yeah, and this is about, we will go to about half, and then we up to that. Yeah. S8 again. Okay, yeah, it generates well here, even pass. So let's do full add now. That's what we're missing. Okay, so next I want to do something a little bit fun. What we will do, we will generate the instructions to memory. We will do some kind of some simple function. First, a function that will return a constant value, immediate value, and then we will do a function that returns first argument. Whatever we send to it will have an argument that is sent to that. So in order to do that, I can write a little test for that. x64 test execution. We'll call it 1, and let's call it ret immediate. We will probably need some things for that, of course. So what we will do, we know that on Windows, this is only for Windows. On Windows, the calling convention says that we can open actually that, but the first 4 arguments are passed via register. So if we do x64 Windows calling convention link, then we know that yeah, so this is for example all integers. So we know that first argument will be passed via RCX, second RDX, third R8, fourth R9, and the rest of them is on stack. We will not deal with the stack just yet. We can do that later. We now have ways on how to deal with stack because we have operations that read from memory, so that thing there. So that's what we know now. And then we have return values, and those are returned when it's integer in array-x. In case it's a float, XML. So what we need to do for target, our goal, return immediate value 1, 2, 3 from a function. So we will do x64 mob, x64, and we will do 32-bit version now, just for now. We can test the other ones as well. x64. So on left, we need to do basically mov array-x 1, 2, 3. That's what we want to do, or EAX, because we are doing 32-bit. So we will do register EAX. We only use 64-bit name. Okay, that we want 32-bit size, that will automatically. And then we want immediate value x64i, which would be 1, 2, 3. Okay, so this thing, the mov instruction, the mov function returns something called x64 inst, and this is just a static buffer count and a possible error. I did it this way for now. Eventually I will probably have some kind of a writer in the API, so you can pass some buffer for your own function and I will buffer on my side, on the x64 side, and when the buffer is full or we're done writing, we'll call your function. Okay, so we will get this instruction. So that's the first one, E0. Let's call it E-mouth or I-mouth, and then we will do ret. We don't have ret yet, but we can do ret quite quickly because that's just single instruction that we can do quite quickly. x64 inst, x64 x64 operand. We don't have any operands, and we will return x64 inst. Bytes will be set to something, and count will be 1, and error is 0. So yeah, this will do the trick. Now we need to find this red thing. Of course, you wouldn't have to do that when you are doing your stuff, unless you want your special instruction that support. But here we see that yeah, we don't care about these. Fuck that. Because these are used. What should I? Far return or near return. I don't know which one. I guess it's don't care about those really. Far one, I guess. We will look at what this thing does. So red. This mode it will do C3. So we will do C3. I don't care. And we will make a note because we probably want to look into these two. CB. I guess CB will be then reused to do with about yeah. So this will return in the same format. We'll return the read instruction. That will be this. So this, we expect this to be in the memory. We encode it like this. Register on the left, immediate on the right, and we want return. Now we need to put it to memory somewhere because these are now distinct two buffers of fixed size each, and we want them back to back. So what we will do, first we will call this thing. Afterwards. Here will be magic, and then we will have a function, and we will call it, and we expect it to return 1, 2, 3. So what the magic is quite simple. First, we allocate some memory, allocate a page from virtual memory. I have functions for those. And I'm not sure I want to risk it right now to actually do it through. We can try it, definitely. Or we can extract it from the function. So yo, come on, C CO virtual alloc. This does commit and reserve to different calls, but I'm sure we can do it just with one call. This one, yeah. So we will do this one, and this is 0. We want on page. I'd say it's let's say it's 4K. This will give us page aligned memory anyway. Just aligns it up to page size, which I guess on Windows it's 4K. Mem commit page read write. So we want. This will be important later. We want memory that we can read and write from. Actually, we can just have a page that we can write to, because that's the only thing we care about from it. That's like the only thing. Yeah. So we will do this one. Memory. Function memory. And we can do it like this. This will be probably the best. So this will give us some memory page. Not actually malloc, it's just a memory. It's what alloc uses to allocate memory from system. This is always called like the lowest level you can get through on Windows. As far as I know, maybe that is over. This will give us some memory. Then we need to copy. We can do it quite simply. We need to copy both instructions to that memory. I originally I will have like two simple functions that will allow you to just write it memory instruction by instruction, or we'll have the writer, but we don't have that now, so we will do it here. I will create an iterator that we can use, and then we will copy IMOF the bytes, copy it here, and we will move IMOF dot count bytes, and we will increase the iterator by IMOF count. The first thing, and second thing, we copy the array. Eventually, imagine this will be wrapped in an easy API, as long as you provide, of course, the memory for it, or will do whatever. But I guess it depends on how we're going to call these functions, or what you're going to generate. First possible thing that you can, simple thing is that you can have a fixed memory. Other thing is that you can just first slap it somewhere in a dynamic memory that can grow, which is either some malloced array and realloced array, or allocate next page with virtual alloc, and then eventually go down and concatenate all the pages to somewhere else. Or you can even remap those pages, I believe. We'll be able to eventually make... I heard that this somewhere, someone sent me a link that you are able to actually remap the virtual memory allocated, so that first you have it randomly in memory, and then you can just go and say that, okay, let's make these several pages appear as if they were back to back in memory. That's quite an interesting concept, and I might even implement it with x64 or some additional library for Windows that will give you these things. Okay, so we now have both of these functions, both of these instructions in the memory, and what we can do is one thing we can do first as well is to use the dump function. This one. We can do this thing. IMOF. Just can simply print it out, see what is there, what actually be produced, what our library has produced, and then we store it to memory, and we'll check whether memory is correct. Then what we have to do is we need to change this thing on that memory that we have allocated on that page, the executable. So I think it's virtual protect function. Yeah, it's virtual protect. Virtual protect, and yeah, it takes address of that memory, so that's for us the function memory. It takes the size, which in our case I think it can be 0. But I'm not sure. So yeah, it cannot be 0. So let's say it's whatever we allocated originally. It might be also the sum of these two, but I think this is okay. And then it takes new protect, which is memory protection constant, and it's one of these. And what we want to do, normally if you would just run the code, you would use execute, but we also want to inspect or read. If it was only execute, then we won't be able to actually see it at all. like we wouldn't be able to take a look at this pointer. Read from it, it will basically go up and etc. We can try it, but let's try it. So this is a new one, and then no, it's not that one. It's fucking hell. Just do what I mean, not what I do. And go back, and finally it's a pointer to D word. D word, which is alt protect, and that's we'll just get the value of what was in here, which should be page right. We can check on that. We can actually do that. Alt protect page read write. Can check on that whether it's what we expect. Okay, so this will make this memory to be executable. Now to execute it, it's quite straightforward. So we need to define a function pointer. We know that we will return 32-bit value, so it will be say 32-bit value. Actually, it will always write to array X register. So if it's 32 or 64, doesn't matter. We can do 64 at the moment, so it's reusable later, so we don't fuck ourselves over. We will call it somehow. So let's say it's int 64. We will call it ret int 64f function. Let's call this one, and it takes nothing. It takes like voids. Okay. So what we will do now, we will basically go and define that function and do really nasty thing of this one. And now when we call that f here, because now it's a function, right? It's a pointer to function, so we can normally call it. It should give us this one, if everything went correctly. What we need to do as the last part is free that memory, because it's now executable memory that nobody can read. I think we can still free it. We have the pointer, so hopefully that will work. So we will do first this function memory pointer, then 0 because it's a size, and we say release. I think this is correct. Just correct me if I'm doing something weird. Okay, so that's function memory, and this should basically just do the trick. So to recap, we generate the instructions to memory. We will print them out to be able to debug whether it's correct in the memory. Then we allocate some memory for these instructions, for that code. We put that code into that memory, change that memory's protection to execute from read write, execute. Now we won't be able to read that memory, I guess. So when we will try to I will have a pointer to it here. When we will try to read from it, it will probably, I'm not sure whether a debugger will cache the memory, at least for the display, because this is fucking HTML, so they cache everything. That's why it's all the memory. So yeah, we will try to get read from that memory after we do project, before and after, and we will see whether we can still read from it to just confirm that it works as we want. And then we will type basically cast that function pointer that we got here, the function, or that raw memory that we have executable now, the function, and then we try to call it, and we expect it to return 1, 2, 3, and finally we free that memory. So this is basically way freeing a function, which is just kind of interesting possibilities when you can generate things into memory, run it as a normal function, pass arguments to it, it will calculate something for you on the CPU. There is no virtual machine if you don't count, of course, micro instruction like that, or micro opcode on the CPU itself, and that's it. So this will give you dynamic functions that you can generate on the runtime if you know how instructions work, on what instructions to use. Okay, so let's do this. No more talking. It'll be fun. Yeah. It's not a What did I mess up? Messed up. I believe. Yeah. Is it though? Function. What? I just did that like a few days ago and it worked. I will do it just this way. If anyone knows what I messed up, let me know. Just feel free. Yeah, so, yeah, okay. Yeah, I'm not using pointers because pointer is already here. It seems to be confused even though it shouldn't matter. Okay, so we have some problem here. Yeah, this is, yeah. I have modified printf, actually stb printf, and it's able to take a special form of a string that I'm using internally for my things, not my libraries that are public. So at this point we are just before the function memory, and we know that the memory should contain these things. It should be, yeah, it's B8, which is mov, and then it's it seems to be just interesting. Okay, let's just give it a try because this looks weird to me a little bit. We are still not doing everything as we're supposed to do. No, we do. Obviously we do. Yeah, I think B8 has. Yeah, B8 has opcode. Yeah. Yeah. Need to confirm. And I think the opcode is the one that encodes register into the opcode. It doesn't need any mod RM bytes or anything like that. So this is B8. Yeah, B8. It's register, yeah. The opcode is there, but because it's array-x, it's 0. So it will be still B8. It will change. Okay, now we can look at the function memory. Function memory, which would be 32. Let's give me 32 bytes from there. And can you give me? No, you cannot. Do x. If I do x here, it will give me the decimals. At least in this window it works. So we have B8, 23, 01, 01, then 2 zeros, then we have C. This will return us back to it. Now when we do this again, can we read from that memory? I'm really interested. I haven't tried this. Obviously still can read, so alt protect is 4 is passed, so alt protect is this one. Not sure what the page execute and execute read does, but obviously it allows us to read from that memory, unless this is cached somewhere, so I don't care. So now we have this function, and we should be able to launch it, and it would return. We can actually do it this way. Int 6040 result will be f, so we can see it. Because now it's just in assert that is doing something over there. So let's redo it. Let's stop right here. Now result is full of garbage, and when we go through it, it will be 291. And 291, because we are encoding 1, 2, 3 hexadecimal, 291 in hexadecimal is 1, 2, 3. So we have a function that returns constant value. Ta-da! And we're done. Okay. So what we can do next is we can play with it a little bit. So we can have a function. Let's create another type that will be taking actual argument, and let's say it's 32 bits. argument. And it takes 32-bit argument here, just integer, and we can change these ones. So, and that argument, because it's the first one, if we call it, we can do, let's do decimals, because decimals will be immediately visible and have to transform all over the place. Let's do 666. Yeah, no, let's do 1337. I think Ruby loves that number for some reason. Know why, but anyway. So we will call this function. We will pass argument to it. It will not do anything at the moment because it's just setting result to 1, 2, 3. But it now is able to take, at least C now knows, because assembly code on this level doesn't care whether you actually pass anything. Just if you have to do all that control in a higher level language. If you don't pass things to it, it will just expect them to be there. Or your code might expect them to be there because it will read from RCX to read the arguments, but they are not set. There will be garbage, and that's it. There's nothing that will check on that. So now we will call the function. It should still work. Yeah, so we can call the function. We pass argument to it. And the result is still 291, 123 in hexadecimal. Okay, we can do also result in hexadecimal if you want, but at this point, once we call these ones, let's leave it like this. So we don't do anything. Now, what will happen if we will change this and we will not do constant value that is assigned to MOV, but we will do instead of this one. So this is commented now, and we will copy the ECX to it. And we know that ECX contains, by the calling convention, ECX would contain the first argument that we pass. This is given by the RCX will have that value of that first thing, that 1337. So we will copy that value to output. So let's do that. So now we are copying the ECX, so first argument to the return value, and then we return. That means that this should now fail, and result should be 1337. So let's call that. Tada! Result is 1337. This will fail because it's not correct, but result is 1337. We can do 9600, for example. Nice number, modern times. Result 9600. Yeah, and it works. Yeah, so this is what we can do. We can also try our add instruction, and we can we can double that value. Basically, we can add array-x to array-x, so we will have EAX. So we will now double that value. So let's keep it this value, and the double will be, yeah, I cannot do that math in the memory in my head. So 9600 plus 9600. So this is the value that we expect to be there. Yeah, and we need to write it, of course. We can also do x64 inst. Or we can just do it like this, right? So this will just encode the instructions to this array. We then can go through that array. We can write it out. What we are putting there. This will be inst I, and just copy it. Inst I. Yeah, it's So this will do the same thing, right? Except we now don't have to keep like several instructions in several variables. We will just create array of instructions and then merge it here and print it out. Here we go. Okay, so this will print out. We can stop right here. Operation. So let's stop right here. We'll print out the values for these things. So it should print out something like this. Yeah, it should print byte codes for bytes for all these. You can actually put this to produce in the thing and compare it. Let's assemble these. So this is what we expect it to be. So let's try it. Oh my god, what happened? Yeah. Okay, so we can compare it with this. For some reason they chose, yeah, they are choosing different instruction here, but it should do the same thing. So if we take these, then here, try, yeah, it will be the same thing. It will be the same thing. It's because preferring different instructions for this case, for register. Than what we do, because L64 and 64 prefers those 8B. So it should do the same thing, right? It should write ECX to EAX, other way around. It's sad that this doesn't keep like both results. It will reset the one. But it will do the same thing that we wanted. Yeah, EAX moves ECX to EAX and EAX to blah, blah, blah. Okay, and at this point we are putting it to memory, so we can take a look at the memory as well, whether it did all we wanted. So it should be 8B, yeah, C1, yeah, O3, yeah, EO, C0, yeah, C3 for return, and then zeros, yes, because this also, when you run the process, it will zero the memory. Virtual one, I think. And that's why conveniently we'll have zeros there, so that's kind of amazing. So now we will convert that pointer function, which takes one argument, and we expect the result to be this thing. So convert and it's that. So yeah, that's I don't know with you, but I love it so much, because you can now produce like a CPU level code from C, and it's useful, and it's very useful for other cases than just languages or compilers. And also generate, for example, imagine that you needed to go through, you are in Lua or some higher level language than C, and now you need to produce some algorithm or some fast way how you can iterate over memory that you have. For example, in Laughter.d, I would use games and just implement ASM instructions and use FFI from Logic to do these tricks. And then in Lua you will be able to produce assembly code or native code and run it, because you are able to run C functions in Laughter.d rather with Logic, and quite nice to have that option. Or you have I don't know, Eric C would use Lisp to and then run that, for example, for audio processing or something like that, right? So yeah, this works, and I think this concludes today's, because I just want to go and relax a little bit, although I have vacation for next week. Relax a lot, although I think that, you know me. Okay, So that's it for today. We now have beautiful thing that seems to be working correctly, and it's also quite useful. Yeah, about the I didn't talk about this. I don't like pushing out code that is not finished just yet. But this library will be public with as permissive license as possible. I'm not sure how it's with public domain in Czech Republic, into which I legally fall under, but yeah, it will be something like public domain or anything like that. I don't plan to be able to sell this or whatever. So this all will be available. It's now in my private repository because it has a lot of mess, and it also has some dependencies, especially the tests have dependencies on my other library. This is my base code basically for all kinds of shit. Actually, here there's a I have all the libraries that I generally use, and this is like a big bunch of big pile of code that I gather over time. It also includes my runtime, which is basically platform layer with DirectX. It works on top of Sokol, or it can work on its own DirectX implementation. So if you don't want so. Also, all the text editor stuff here, it lives inside of this thing. This is all the text editor. So Rift, basically part of that library. I will eventually will have to make it public, but for now it's like this my own little thing, and I don't want people to really submit PRs or whatever. Fixing things, yeah, it makes sense, but adding features, I'm not sure, because this is really just like. So I want to make sure that the library doesn't depend on that. Eventually, I think it wouldn't. Most of the things are these log things that I do. Maybe I can just change them for printf. Then there are some little things with asserts and checks and fails and things like that just are done in the way I prefer them to be done. Using the default ones from the standard library just doesn't give proper information when something goes wrong. Okay, so yeah, the debugger thing we can do next time to do the debugger thing. I will tell you next time. Well, but it will be probably Thursday or Friday, maybe next. Up until Thursday, I will be completely different than Prague. Okay, thank you guys very much, and yeah, I will just push this out and take care for the weekend. Have a nice rest of the Sunday, and see you in about a week with this stuff. Bye bye.